That's perfect. Usually we don't get through all the questions. So we'll save the chat and then we'll send it to you for your information afterwards. But yeah, Q&A has been just great, right? They ask many interesting and thoughtful questions actually. So we've been very impressed by them so far. So.
Great. And so I'll just, I'll keep an eye on the chat and then interrupt, from time to time and let the students ask their questions when they come up. And your name would be pronounced Regina Apodaca, or okay, excellent. And how far along are you in your PhD? I'm just curious.
Well, I just finished my 3rd year, so
okay.
Yeah. But my master's project and my PhD project are not entirely overlapping. So, that definitely adds a couple years.
Oh, that's great.
Oh, and then we'll have the recording on the YouTube. So what we'll do is that Joel will actually edit out the beginning and ending a little bit and then share it with you so you have a chance to review it one more time, and then we'll post it, and then we also have to do the closed captioning properly by MIT video. So, but we have 2 weeks to do that. So we'll bring it online, as soon as Joel gets around to it, so within a couple of days. Yeah.
Oh, okay, that's good to know, because I was gonna try to use, so PowerPoint has a closed caption, automated closed caption, but it's not great. So would you prefer me not using that so that you can just
I don't think you need to use it. So when we post on the YouTube channel, there is a YouTube as a feature, but apparently that does not meet the minimum standard of MIT regulations. So we actually have to have a MIT video productions go through, and they turn around really fast, clean it up, and then we'll just post it.
Okay, so I think I'm good to go. If you guys need anything, I'll be in the background, and I'll reach out to the students just to make sure they know about the final phase.
I guess they're still slow MIT time. They think they have extra 5 minutes to join.
We'll start letting them in when they get just close to 300. We're almost there.
It's been crazy during these Zoom times having such large audiences. Because, for me, it's so easy to talk because I only see you 5. And
right.
Actually, it's so many more people.
Yeah. I think at the beginning, when Dan does the introduction, you'll have a chance to see all of them. They're just a great bunch of high school students. Yeah.
I'm going to start admitting them.
As we're waiting for everyone to get in, I just want to remind everyone to chat your name into the chat if you haven't done that already. All right. Well, I think that we can go ahead and get started. I want to welcome everyone to what is the last seminar of the seminar series. That's fantastic, and I'm really excited that we have Regina Apodaca here today to be giving that last seminar. The title is "Learning How to Fly in Mars and Space," which sounds really cool. I'm really excited to hear all about that. So Regina is currently, I guess, finishing her third year of a PhD program in the Space-Enabled Research Group at MIT Media Lab. And she has also done a master's at the MIT Aero Astro Department, and also did her bachelor's in physics from the National Autonomous University of Mexico. And she has a broad set of interests and experience in topics ranging from space propulsion, fluid dynamics, and aeromechanics, astronomical instrumentation, observational astronomy, and theoretical astrophysics. So I'm really excited to hear what you have to share with us today. And the way we're going to do today's seminar is Regina would love to take questions as we go. So if you have any questions, please just type them into the chat, and I'll try to keep an eye out and ask you to share those questions as we go. So Regina, take it away.
Thank you for that lovely introduction. I'm going to start sharing my screen and do your classic awkward. Can you see it? Okay. Oh, it's okay. Are we good?
Looks good.
Oh, shoot. Okay. Sorry, started on the wrong slide, but here we are. Hi, everyone. My name is Regina, and I will be talking to you about learning how to fly in Mars and in space. Just a quick overview of all the topics I'll be talking about. I'll give a quick, brief introduction to my story, talk about all the research opportunities I've had and where they took me. Hoping that you identify yourself in these stories or see how exciting it can be to do research opportunities. I'm not entirely narcissistic. So then I want to talk a little bit about ingenuity and the role I played as part of this team. I'm going to go into my master thesis, which was a space propulsion, electrospray thrusters, then go into wax propulsion and finishing on zero robotics, which is an awesome project that my group is taking on, and would love to invite you all because it is actually targeted to high school students. Okay, so as I said, there's tons of different topics. So please feel free to interrupt and ask questions as I go, because if not, we're all gonna get confused and messed up. Okay, quick introduction to Regina. So as I said, I'm Regina and I'm originally from Mexico. So I always like putting this picture, this little picture of me and my sister, because this is, I think, what everybody thinks growing up, people that end up doing space propulsion or space related things are like. This is actually quite funny because I did not have any sort of interest. Well, I guess I did, but not like set in stone until much later. Actually, it wasn't until my last year of high school when I actually started asking myself, what do I want to do with life? And I was in life. And I remember watching this documentary called Cosmos in my physics class and being completely fascinated by it. And then running to my physics teacher after school, being like, sir, what can I do to learn more about that, about cosmology? It sounds amazing. And he's like, well, the first thing you have to do is be incredibly smart, which you're not. So probably look for something else. And this was very hard for me to hear. But as I said before, I'm not entirely narcissistic. So I was like, he's right. I know a lot of smart people. I know people that are building things since they were 2 years old. I'm probably never going to be that smart, but that's okay. I'm sure there's something I can do to help them. And it was going down this rabbit hole of what do cosmologists do and how can I help them, that I actually discovered my true passion, which was instrumentation. So in my mind, I was like, okay, well, if I'm not quote unquote smart enough to do the data analysis, at least I'm going to help them by building the instruments that they need in order to get that information out. Here I have a picture of me in, me in front of my alma mater, which is UNAM, or the National Autonomous University of Mexico. And the reason why I put this is because for me, it was very important to study in my country. And I'm a very proud Mexican. I'm very proud of my country. However, I acknowledge its limitations, right? I come from a background of women so my family, I grew up with only my mom and my grandma and my aunt and I was raised as someone who had to always look out for everyone else. My family didn't believe in me going into science because they were like, what do scientists even do? You should do something that helps the country, you know, like be a lawyer, be a doctor. Unfortunately, you know, the idea of taking care of living things is something that's very stressful to me. So being a doctor could not be a thing. And like being a lawyer actually was what I wanted to do for the longest time, until I actually realized that the importance of science and technology. I knew that I could give back to my community by bringing these technologies that now, like, not only can we have cameras to look at stars, but these cameras can also be pointed down to Earth to look at natural disasters or to study the change that we're having into our environment. So, you know, I very quickly dismantled this idea of, you know, science not being actually helpful. So here's a little to the Harry Potter fans, fantastic research opportunities and where to find them. As I was going into, as I was finishing high school, I had the amazing opportunity to apply to the Weizmann Institute of Science. It is a research institution in Israel that hosts a program every year. Write this down because you are actually capable of applying. It's called the International Summer School of the Weizmann Institute of Science. And it is a fully paid, fully funded trip to Israel to do research for a month. And here's a picture of the 80 students that were there. And this just truly opened my mind, not only to the type of science that we can do, but also the community that you get to learn and meet. So you apply, and I got to spend a full summer studying about dark matter detection. Please do not ask me too many questions on this because this was so long ago and I'm no longer an astrophysicist. But, you know, it was a very important moment for me because this was the first time I ever won anything in science, right? So it was the first time that, you know, somebody that actually knew science was telling me that they thought I had potential in it too. So that was very important to me. But the second most important thing I learned was not all science is what I want to do. And it was also a very important thing. In this project, I was doing simulations. So what I was trying to help was find the optimal geometry within this detector that would allow for the least level of false detections. And it was all math things sitting in front of a computer, which I do a lot of right now, especially during Zoom times. But that was the first time when I realized I love science, but I love building too. So that's where I realized, you know, I am a physicist, but I may also be an engineer. My next stop took me to a completely different part of the world. And I actually ended up going to Australia. As I said, I realized that I was going to be that I wanted to do instrumentation, but more than that, I wanted to be an astronomer. So here are a couple of pictures. On this side, there's the group of interns that were there. I mean, I'm sure you are having this experience now, but all of it, this was actually the first research opportunity where my mentor sat me down and he said, I'm going to teach you about science. I'm going to teach you about astronomy. But the thing that you have to teach yourself and the way you're truly going to benefit from this research opportunity is if you go out and meet people. Introduce yourself, talk to researchers, ask them what they're doing. And I was like, but I'm an intern, I could never. And he's like, no, everybody loves talking about what they do and their research. Like they're just waiting for an opportunity to talk about it. So if you can take anything from the conversation I'm going to have you is, number one, look for research opportunities. The US has so many, but the world also has a lot to offer. So, and a lot of these, so this astronomy program was also fully funded. I was paid by the astronomical observatory to go do research with them, which was a huge opportunity because people value the work that interns do. what you're doing now may not seem huge to you, but for a lot of research programs, it really does matter what you're doing. So this picture is actually really cool because it's the reflection on one of the major mirrors of the of the telescope that I was working with. And this is a picture of me pretending to be working with the telescope. In real life, there was actually my advisor sitting there, and I was sitting next to him because, you know, I was still learning the ropes, and he wanted to make sure I wasn't going to break anything. But, you know, he allowed me to sit in the main chair just to take a picture. Okay, I feel like I'm going a little quick. I'm going to give a brief talk about what the telescope I was working with was doing, and then I'm going to pause to see if we have questions. So as I said, I was working in a telescope, but most importantly, I was working on a detector that was going to attach to this telescope, right? So when we think about astronomy, we think about, you know, these big buildings, but those buildings have the capability of putting a whole bunch of different instruments that specialize on different things. So if you've been going to any sort of like astronomy project, you know that the buzzword right now is exoplanets. We all love talking about exoplanets. And the new, the novelty of this is probably better described by exoplanet experts. So I'm going to talk about a little bit about my contribution to this project. So I worked in the spectrograph. So it's this instrument that's attached to the telescope that allows us to measure the difference in radial velocities caused by the presence of an exoplanet. So basically, as we see here, the little planet moves. Obviously, this is exaggerated, but the mass of the exoplanet moves the star. So that causes it to like shift back and forth in our perspective. And those changes are the ones that we are measuring. And what I did was help in the design and selection of these little lenses and gratings. This is actually very interesting to me because I always assumed that, you know, there was a program out there that you just kind of told it this amount of space you had, but it was actually a lot more artistic. I remember growing up being super jealous of my very artistically inclined sister and feeling like I couldn't draw past a stick shift. Sorry, a stick figure. So when I discover CADing and I discover designing instruments, I see that there is this art to it, which was very exciting. Okay, I'll stop there and see if you have any questions.
I'll ask a question. So do you know, was that spectrometer built, and do you know if it was involved in detecting any exoplanets?
Yes, this experiment, although it was designed and built in Australia, it actually went behind one of the telescopes in Hawaii. So yeah, there's a very exciting paper where we do get to see a lot of these. So this technique is actually very commonly used. What was special about our experiment was that we were focusing on infrared infrared stars, right? So the ones we can see with our eyes are emitting in the visual, but the ones that we can't see because they're in infrared, those are the ones that are most common, and that's why we decided to focus on those.
Cool. I see some other great questions. So Isita Talukdar, do you want to ask your question?
For sure. Thank you so much for coming to speak with us. Like, so far what you've been talking about is really cool, and it's like really inspiring, like how much work you did. And as an intern, like it really cleared up my perceptions of how much impact like interns have. And my question is, what was one of the biggest changes that you faced when you left to study abroad, or one of the most memorable ones? Because it must have been a big experience.
Right. Honestly, I think one of the biggest difference was the imposter syndrome I felt. I definitely, going somewhere else, I think put a lot of pressure, right? Like for the Australia one, it was the Australian government that was funding me. And I was like, why would they fund, you know, a young girl from Mexico who like was told by her physics professor that wasn't good enough for, you know, for anything. Like it was very hard. And I think especially going to Australia, you know, it's such a huge time difference for my family, and the flight was so long. There's a lot of self encouragement that you have to be doing constantly, right? Like I realized that, you know, I was going there and I wasn't going to know anyone, but I knew that I was, you know, that I was capable. I didn't know, but I kept telling myself, just remember that somebody thinks you're capable. Just remember that, you know, at some point you didn't have friends when you first started undergrad, and then you made friends, right? Like, I think, you know, you just have to mentalize and say, yes, it's going to be scary. Yes, there might be a lot of issues, but you are capable of solving them. And you're not alone, right? You have different mentors, and you have other interns that are there that are probably equally as nervous as you, even if some might pretend like they're not. So just know that you're not alone. And if you are for a split second, I'm sure you'll find someone.
Okay, let's see. Chris Good, do you want to ask your question?
Yep, that'd be great. Thank you. Hi. So yeah, my question is, you know, what kind of subjects or physics courses should I take as an undergrad if I want to kind of study this stuff? And you know, as a kind of like follow up, what you have on the screen right now, you know, there's so many different kinds of things, from Doppler effect, which is related to waves, to I even see some light optics, ray optics, and stuff like that. So would you advocate for like a diversity of physics, like learning all kinds of different physics things, or is it really just more kind of linear and very specialized?
Right, that's a great question. And I'm so happy you asked it, because I think that was something that I really struggled in as a high schooler, trying to decide what I wanted to do. As I said, I decided pretty late in my mind, right? Like pretty late in the game, that I wanted to go into physics. So I felt like I didn't have the information I needed to make a good decision. However, as I said, for me, it was very important to do my undergrad in Mexico. And at the time that I was applying, especially because my university was free. So that was a huge, like not having the financial burden was a huge thing for me too. So I was really trying to find a way to like meet all these expectations apart from just following my passion. And that's why I decided on physics. Because although I knew I wanted to do aerospace engineering in the future, I felt like if I did any other type of engineering, I wouldn't have the background that I needed, right? Like I felt like if I went too into electrical, I wouldn't have the thermal side of it, right? Like if I went too into mechanical, I wouldn't have the electrical. So that's why I decided to do physics. The two main advice that I got from my undergrad professors, and they're kind of conflicting, but I guess like the idea is just do whatever you feels right. One of them was, there are a lot of intro courses that are good so that you can identify if that's what you like, right? There's like intro to astronomy, intro to optics. I was someone who did all of these because I wasn't sure, right? Because I felt like I didn't have that previous exposure to science, as, you know, because a lot of when I went into undergrad, a lot of my, you know, fellow students had, you know, professors who they had talked to, and, you know, and I had no idea. So I was doing all this kind of blindsided. But then there's also the strategy of getting a lot of math in. In everything you do, the hardest part for a lot of people is going to be math. So when in doubt, having a strong math background is going to facilitate moving forward. And I say this as I struggled through every single one of my math classes. Like they were really hard, but it is true that struggling through that in class made it so that in my research, whenever a math equation comes up, I feel prepared. That's not going to scare me away from the topic. So I think having a strong math is very important. Testing out the intro classes of any topics that you're interested in. And the third and final is asking older students. I'm like, asking students who have taken the class, asking them what they saw, read the syllabus. That is all very important, because at the end of the day, this is your chance to form your own education for the first time, as opposed to like high school where you're told what you have to take. You're making your own career. So don't take anything just because somebody like says you have to do it, because it's also interested and you see it as an investment on yourself.
I see. That's such awesome advice. Thank you so much.
Thanks. And then I think there are two questions which are kind of related. So I might have, Adarsh and Akshata, do you want to both ask your questions, and then Regina can ask them, because I think they're related?
Sure. So I would love to be able to take part in these high school research opportunities, but do you think it's already too late for a rising senior like myself or most people in this call? Right,
and then before you answer, there's a related question to Akshata.
Yeah, so I had a similar question, but I also was wondering, based on your experience, what advice do you have for students just starting into research? And how would students like us find research opportunities at this age?
I am so happy you're asking all these questions, because I was wondering those things too in my last year of high school. As I said, it wasn't until I was an actual senior that I decided. So it was, there's tons of opportunities still out there. What do I recommend? Okay, Google, there are some key phrasings like research opportunities, summer schools, summer internships, all of these learning, like first it sounds silly and it sounds condescending, and I'm really sorry, but it really isn't. Like, it's just learning how to Google and just read through everything. There are going to be tons of them. Put high school summer opportunity, high school summer internship. These are all very important. My first research experience was, I didn't put it here, which I should have, was actually with my alma mater. I had a friend who said he had emailed a professor in astronomy and was willing to talk to us about it. And it was literally like he just emailed this professor from our local university and said, "Can I talk to you?" And it's crazy, again, it's crazy how they do reply. And I know it's very scary, but I think for a lot of researchers, the fact that you're even reaching out to them shows a huge promise in your capabilities, right? And your belief and willingness to work. So I know it's scary, but reach out to professors or reach out to grad students. I'm sure maybe students, they're a little more chaotic, but they'll probably also be willing to help. So no, it's not too late. There's tons of opportunities. So actually, when I went to Israel was in the summer between high school and undergrad. So I was already, I guess, but I applied during my senior year. So I saw someone in the comments said it's 18 years, so that's after high school. No, it's been running for 18 years. I think when I went there it was year 12 or 13th. So it's been going on for a while. But yeah, there's tons of others. And yeah.
Okay, thanks. Why don't should we take a couple more questions on this, and then let you go ahead? Maybe Ozan, do you want to ask your question?
Yeah, sure thing. So my question is, what has been the greatest takeaway from your experiences doing research around the world, and how have these assumingly different experiences affected your understanding of the research process?
What?
I just
Yeah, no, thank you for your question. I loved it. I'm someone who truly believes in the value of diversity in and representation in the people that you work with, and the location that you work with, and the topics that you work in. Any sort of new and fresh ideas and interactions you can interact with are so important. So for example, I remember, so I'm going to talk about it a little bit later, but going to NASA, right? And everybody being like, oh, it's so bureaucratic. And for me, I was like, are you kidding me? You can order a part and it arrives in the same week. Like working in Mexico, like I had to wait weeks, like even months to like for a part to arrive. So, you know, it's a different of perspective, right? Like in Australia, similarly, you know, like our close telescope was a 6 hours drive into the middle of nowhere, right? And everybody like would do that weekly. They would do this like in 2 ways, right? So they're spending 12 hours, and it was just, and like for me, that was like that idea of driving such a long distance weekly was horrifying, right? And it was just something that they were used to because that was part of their research, right? Like how you do things and how people interact and how, yeah, I guess like the privilege that you have in your environments and like the struggles that you have are going to be completely different to that in another country. And I strongly encourage you to do so, because more than that, like I didn't know about summer research opportunities. Like this was like the first one I went to was kind of like by accident. And meeting people, they were the ones who told me that this was a thing that people did every summer, right? And I was like, what? That's insane. And like, you know, if it wasn't because somebody told me that that they would pay me, that I found out that my work was worth something, right? And like, not only that, like, but it was available for like low-income people too, right? Because like, I don't know if I could have afforded living in Australia for, you know, like making money in Mexico, right? Like the wages are so different. Like I was really nervous. So I think that's what I learned. I learned that there's more than one way to do things, and that we all struggle and have privileges that are different. So.
Okay, thanks. Awesome. So why don't we, I guess, why don't we continue, and we'll get back to questions as you go.
Okay, thank you. Yeah, so after my amazing time in Australia, I got to work in LIGO, which is the Laser Interferometer Gravitational Wave Observatory, which is here in the US. So this is my first opportunity to come into the US. And this is important because I got to work here primarily because my mentor was the one who encouraged me to apply. And like, you know, my story is a little bit about how I was not self-confident enough to push, and I was lucky to have these people encourage me. But you shouldn't wait until somebody encourages you. If I believed in myself as they believed in me, I would have been able to find these, and I would have been able to push. And I want you to know that it's true for you too. But here's my first opportunity to come to Caltech. And I worked in this project, which recently, well, I guess not so recently, but won the Nobel Prize. And it was very exciting. And it was a huge collaboration. And the contribution I did was this tiny, tiny part, which is, as I said, it's a laser interferometer. So it uses these very high power lasers that, and one of the qualities of lasers is that they're very thin, right? So whenever you point them at something, the amount of energy that you are transmitting into that optics is huge. So obviously, whenever whenever you warm things up, they start to warp, right? So that's kind of what we see over here. Like the single laser was warping the mirror and therefore was creating some optical anomalies onto it. So what my advisor was thinking or was doing was we were projecting an even higher power beam around it that would deform the rest of the mirror, right? So instead of avoiding one thing from deforming is, well, if we deform everything, it's actually normal again. So that was our strategy. And what I worked in was trying to test these MEMS arrays to see if we could use them to actively constantly be modifying this warping, which was really fun because, as my friend when I was there would say, is I would shoot things with lasers and see if they would blow up. Because as I said, these are very high power lasers. So we were trying to use off the shelf components and we wanted to make sure they wouldn't blow up. And I was like, well, if I do my research right, they won't be blowing up. But this was very exciting. And it is actually, you know, a real life application. I got to see the actual experiment. I got to talk to a lot of people. And like the best part of this story is that my best friend here in Boston at MIT right now was a girl that I met in this program, right? So internships and like the friendships that you make on them are so encouraging because you're for the first, I don't know, I guess, I don't know what your experiences are, but for me, for the first time, I'm surrounded by people that are equally as passionate about topics, similar topics as to me, right? And that leads us to feed on each other's excitement and end up in exciting places like MIT. Okay, so that was all my my research opportunity. And now I wanted to talk about and go a little bit more into depth about my undergrad thesis. So I'm just gonna pause real quick and ask if anybody had previous questions on what I was saying.
I'm just looking. We're probably we're probably good to go. I mean, I'll just ask myself as someone who personally likes shining lasers at things to blow them up. So did you blow up a lot of optics doing that?
Yes, yes, and actually, it's a funny story because I guess it is important to share. Yes, I did get to blow some things up, but this was the first internship where I broke something that was research related, and it was very stressful. But I experienced it was this one of the arrays. I accidentally dropped it, and that thing cost $300 or $400, which, you know, when you put in perspective of your money, I was like, I can't afford to pay this, right? But like, obviously in research, it wasn't as bad. But I remember telling my advisor, and he sat me down with like a whole bunch of researchers, and everybody went around the room telling their story of the first time they ever broke something. And, you know, and it was just this wonderful experience of like realizing that like he's just like, as long as you don't break the same thing twice, doing exactly the same thing, right? Like the idea of research is learning from your mistakes. So he was like, if you keep breaking them the same way, then you're not learning anything, right? Like similarly, like if I kept shining the laser in the same power and it kept blowing up the same way, like, you know, what was I learning? I wasn't learning, right? So I guess like my story to you is, everyone you see doing amazing research at some point broke something for the first time and had to tell their advisor. And, you know, some stories ended up with, and they kept working in hardware. And some stories were like, and I never dared to touch hardware again, which I hope that's not the reason why you don't go into hardware. But I just thought I would share that fun story. Okay, so then I'll keep going to my Ingenuity versus a Martian dust. So as most of you might have heard, Ingenuity is this little rover that is flying, sorry, not rover, sorry. It's this little drone that is flying alongside Perseverance, our little rover. And it was very exciting because I, you know, got the opportunity to do a 6-month research exchange program with NASA. And I was part of the team at NASA Ames that was working on the flight simulation. So we were in the aeromechanics branch working. Normally, my team specialized in Earth flying helicopters and not Martian helicopters. But who's an expert at Martian helicopters? Well, now there's an actual team, but back in the day, there was no one. So what our team would do for the normal helicopters on Earth is we studied something called brownout. So brownout is when a helicopter is trying to land over sand. And it happens a lot here on Earth, right? Like especially with the US, with their helicopters landing in Afghanistan. tons of sand is lifted up and it causes a giant cloud of sand that unfortunately occasionally leads to a loss on the helicopter, right? Because if you are inside this helicopter and the only thing you see is sand, well, sometimes it's hard to lose perception from how far away you are from the ground, and there's unfortunately a lot of crashes. So it's very important to us to understand how that works, what is produced, and how can we make equipment that can resist that sort of dust. But as our helicopter is going to Mars, what we were wondering, is this a possibility? Mars is a sandy, arid location. Does that mean that our helicopter might experience brownout? Well, this was actually a question that I got to ask for the first time. I remember as an intern, I was working on something else. But this was a question that as I was reading what the team had done in previous things, and I was like, wait, isn't it crazy that this could be a possibility? And my researcher was like, oh, well, actually, we don't have the data to think it's not going to happen. He's like, we don't have the data to think it will happen, right? Like, this is a question that needs to be answered. So this is the first time I ever came up with my own question. And it was, I don't know if you feel this as interns, but I always felt that I was given the questions because I wasn't capable of detecting what a good question was. And I realized that the best way to know if you're asking the right questions is to ask them and see if they can be answered. So that led me to my contribution in the Mars Helicopter app, which is, how can we help study the dust interaction of this helicopter? And what I did were 3 types of experiments. So the white light dust experiment, which consisted of me designing this model of the helicopter and putting it in this box, because obviously people at NASA didn't want me throwing sand all over their floors. That's why it's in a contained box. I did a laser wall experiment, which is basically the same thing, but a different type of visualization technique. So if any of you are interested in fluid dynamics, this is something that would be very exciting because I use multiple different visualization methods. And this is the Tuft visualization experiment. So I'll show you a little bit of the results. So here we see, I don't know if you can see it very clearly because it's very fast, but this is my little model. And I turn it on and I see if it pushes any dust away. For those of you who have great eyesight, there is ever so slightly a change in the dust and clouds, but most specifically, I did image analysis. So I compared an image without, dust, and then the image of where I saw the biggest dust cloud, and overlapped them and took the difference in the pixel intensities to see if there was in fact dust. And that is what I'm pointing out here. So we saw some dust moving. The next part of my experiment was the laser dust results. So, and similarly to most of the experiments, experimental work, you're always going to want to compare your results to a simulation. Why? Because the better simulations we have means the better understanding and capability of simulating what we can expect in real world. So that's why it's so important to compare. As I said before, simulations have never been my thing, but I always see them as a means to an end. So if you know how to do simulations, if you know how to program, that is an amazing skill to have. Put it in your resume right now. If you don't, start Googling how to code. And it's something that, fortunately, is something that you can start learning on your own. So here's another experiment of my laser experiment. As I said, I shone a laser wall onto this so I could have a cut, a cut of the dust. And what you see, these little arrows are showing in which direction the dust particles were moving. So you can see it kind of twirling, which kind of coincided with the simulations I had. And then lastly, I had these visualizations, which again, were just to make sure that we were capable of simulating what we were seeing. So these are actually very cool tufts because they're actually micrometers thick. They're tiny, tiny. They're like as thin as your hair. But when you shine on them UV light, their glow makes them look millimeters thick. So it makes them look a whole lot much larger, which makes it possible to visualize an effect without putting chunky things that might influence or affect the flow of the phenomena that we're trying to study. So I'll pause there. The conclusion was, no, we're probably good. And, you know, the successful flights of our helicopter made it, you know, validated all of these results. And more than that, it validated me in knowing that I was not the reason why the helicopter did not fly. So yeah, I'll stop there.
Okay, any questions on this topic? I'll just ask one. How did you know, was there previous information about what the dust makeup on Mars would be like to enter into your simulations and experiments?
Right, this is a great question. So there have been previous missions to Mars. Unfortunately, nothing has ever come back from Mars, right? So we do not have physical things that we can test. But when doing the experiments, a lot of the things that you have to ask yourself, if you don't have the real Martian sand, you have to ask yourself, well, what of the Martian sand am I trying to represent here, right? Like, I wasn't trying to represent taste, right? Because that didn't pay into account into this. So I didn't have to match that. So I knew that what I had to match was Mars has a very different atmosphere than the one we have here on Earth, right? Mars' atmosphere is primarily CO2. While here on Earth, we have nitrogen and a whole bunch of other things. And that difference in density of air versus the density of the sand, that's what I was studying. I was studying this interaction and difference between size particles and densities. So I had to make sure that what I was doing experimentally was matching those properties of the sand, which you're never going to guess what it was. So the simulant that I used to simulate Martian sand here on Earth was crushed walnut shells, because it was light, and that's what represented the density and the difference in gravity and the difference in, and it was just this like crazy complicated simulation that we were thinking could be reduced to something that apparently is also used for cosmetics. I was very confused, but the only place I could buy it was through this pharmacy, and I was like, what do people use this for? So a very exciting. When you bring down the science, you really notice that it's not as complicated as we think.
Okay, let's see. There's a question from Joseph. Do you want to ask your question? And by the way, I also just want to mention it's about 1:16, so there's probably about 10, 12 minutes left, so just to keep in mind.
Yeah, thanks. So yeah, I also did some research into like Martian gliders, not the Martian helicopter, but I did do some like reading into that for my literature review. And one of the problems that I was looking in the paper was that different Martian seasons, basically the Ingenuity helicopter takes like almost a day to charge up the battery for like just 3 minutes of flight time. So I guess using your software, how do you simulate different temperatures and seasons? Obviously, because you can't really fly in all seasons because Martian, like the seasons are different from the Earth. And how are you able to like detect the temperatures of those particles and like the densities? Yeah.
Yeah, thank you so much for your question. I think, yeah, you bring up a really important point, which is Mars is crazy. Mars is so different to Earth, right? Like, not only do we have seasonal changes, but we also, in the day, the temperature ranges are ridiculously high, right? Like, it's so cold at night, and actually it's incredibly, quote unquote, incredibly warm during the day, right? And this temperature gradient actually made it so that we had to be very careful with our simulations, but also our material selection for the actual helicopter. How did this play into my simulations? Well, the temperature and the temperature played a role in the density of the atmosphere. I guess that's mainly that's the main differences that I'd say came into my role, right? You're right, it does take a really long time to charge, which meant we had to make sure that we were very efficient in the time that we did have to fly, right? We had to make sure that we had enough power to move, and how fast could we move. And that was actually one of my first intern project, was asking the question, how fast can we move at different pressures and atmospheric densities, right? Because if the higher you go up, also the more like the difference in atmosphere. So tons of different questions. Great thing. The best answer I can give you is pressure was how I put it into my simulations, and worst case scenario was what I played with. So for me, obviously, when there's like the density of the air is less, then the less likely we're going to be lifting up dust. So when it's higher, that's when I was asking myself, okay, what if we have great, like great wind, small particles, everything is made so that we can lift dust. How bad does it get? And that was a question I was answering. And the answer was not that bad, but yeah.
All right, so how do you want to deal with the time? There's probably about 7 minutes left. Do you want more questions now, or do you want to go on for like 5 minutes and then take some final questions?
Yeah, I think I'll go into my propulsion, because I've
Good.
Yeah. So part of my talk was, learning how to fly in Mars. So this was me learning how to fly in Mars. But the next part of it is, how do we fly in space? So for my master's thesis, I worked in things called electrospray thrusters. And electrospray thrusters are these tiny, tiny thrusters. They look big in this picture, but think of a quarter of a coin, a quarter coin. And that's actually bigger than these little guys. It's a 10 centimeter by 10 centimeter little thruster. And the idea is that this can help move CubeSats. So CubeSats are these little, this is 1 centimeter by 1 centimeter. The CubeSat is 10 centimeters by 10 centimeters units. And the idea is to modularize spacecrafts, right? Whenever we think of like these big missions, I heard you got a talk from TESS, and TESS is an enormously big project, right? Like we're talking satellites, like the Hubble was like the size of a school bus, right? Where these satellites not only make it incredibly difficult to get anything up in space, but also incredibly expensive, right? So the smaller you can make things, the more accessible and financially sustainable they are. So this project was part of the Space Propulsion Lab, the lab where I did my undergrad thesis. And what we were trying to do is create an alternative propulsion system for these systems. And why is this important? Because if my little CubeSat can do and can move as much as a big satellite, then that means that I can do very important and interesting technology. And this is huge because nowadays there are universities that can afford this. But not only that, a lot of countries that for the longest time have not had access to to space are now starting to produce their first Earth observing satellites, right? And they like to study things that benefit their countries, like how is their climate changing, and and there are companies that are trying to find a way to provide cheap and accessible internet to all the world, right? We might have our difference in mentalities, but all of this is pushing technology to the limit. And what the Space Propulsion Lab did was use the electrospray thrusters mentality. So this is, think fluids with electrostatic fields. And basically what this is happening is we had these cores, tips through which are what we call ionic liquid, which are just liquids that have free ions within them would go up through them through capillary forces, and then they were extracted out by putting them in an electrical field. This electric field, as I said, would pull out the ions based on their charge, and that ion is what we threw out of the thruster, right? Like if you think about conservation of momentum, you're all high schoolers, so you probably have heard of this. The idea is that you have momentum is mass and velocity, right? So if what we do in propulsion is we throw out of our rockets tons and tons of mass at very high velocities. However, because the mass of these things is so heavy, applying them or throwing large amounts of velocity, applying a lot of velocity onto these particles is very hard. However, ions are as big as electrons, right? We're talking about these tiny things that we cannot see. So making something so light move incredibly fast is the technology that is used in these systems. However, I realized that while working on this project was that I love propulsion, but I don't have the patience to work with very tiny things. As I said, all of these experiences have taught me things that I love doing and things that I am not very good at. And tiny, tiny things are things that I get very stressed over. So I decided to go bigger and go into wax propulsion. So wax propulsion is what I'm currently working on. And this idea is, what we are trying to do right now is figuring out how to use wax as a fuel in space. And if you're asking wax, do you mean candle wax? Yes, exactly. I'm talking melt down that scented candle of yours and then light it on fire. Don't actually do this, I'm just kidding. But if you light it on fire, you can use it as a propulsion system. And that is what we want to do. And the idea of using wax as propulsion, specifically our dream of our lab is to use beeswax, is that beeswax would be a sustainable an organic material that we're using. And not only that, but beeswax is something that is very commonly available in so many countries, right? So the idea of making this technology accessible around the world is something that is very important to us because we want to make sure that as a society, everybody can make it to space. However, as I said, wax is wax. So, you know, when you drop that candle and it breaks, that also happens to us. So that's why currently rockets are made out of candle wax, because the vibrations and forces that these experience as they lift off tend to cause it to break. So what we're trying to do is create an in-space manufacturing system so that it can break, it can break all at once as it leaves the atmosphere. But once it's there, we can produce this shape that we want and then use it as a propulsion system. So this is a fun little video of us doing an experiment. And what we want to do is create like a straw of wax, right? So what we're doing here is we're spinning it at different rotation rates to try to determine at what rotation rate we finally get this smooth annulus, which we need. So you can see it's starting to converge into this annulus slowly. And once you reach the final velocity, you see this smooth shape, which we need. Now here's a fun video that was taken by my researcher of his PhD work. So what he's trying to prove was that you could in fact do propulsion with the experiment with wax, right? So I felt like I needed to show you that it does in fact light on fire and it burns like a rocket. And this is true. And it is so exciting because this is something that was considered, this was actually the second place to what was the technology that was being considered for Mars sample returns. So that's how promising this was. Lastly, lastly, I just want to talk about how,
I think there's maybe like, if you could try to wrap up in 1 minute and then we probably have to wrap up. Okay.
Lastly, so one of the big things in space technology is technology readiness level. So you can't just build something and launch it into space, because NASA will not allow you to do that. You have to make sure that what you launch to space will not hurt or damage other things that are already in space, especially if you're sharing space with other things. So in order to do that, you have to do a whole bunch of different steps before sending it. And this slide just shows a couple of examples of what our team has been doing. So first was we wanted to prove that it worked in microgravity. And now for the first time this month, we're going to be sending something that crosses the Kármán line. So it's technically going to go to space. And then our next step, once it's actually been to space, we're going to send it to space for a long time into what is the International Space Station. So if you're wondering how to get involved with space things, I was going to end, and I'm going to throw a real quick plug to this program that is called Zero Robotics Competition. So the Zero Robotics Competition is a programming competition that allows middle school and high school students to learn coding. Remember how I was talking about the importance of coding? This is why. And you get to solve different competitions with your team. So it's a group that you can be part of. And the idea is that there's a task that these little robots have to accomplish. And in previous years, what would happen was the winning team would get to send their code to Spheres, which are these 3 robots that used to be in the International Space Station. So you are going to be sending your code into space, which was very exciting. Currently, our hope, our vision, and our dream is to transition this project into AstroBee. So AstroBee are the new robot interfaces that are currently in the International Space Station. And our team is working really hard to get you onto that project. And once we are, or if we are, then you will be able to send code into space. Having these sort of competitions in your CV is really, really good, because not only does it give you a task that will allow you to better your programming skills, but it also allows you to talk to really cool people like astronauts. Okay, I'm done.
Okay, I'm really sorry that we had to cut this a little short. That was fantastic and really inspiring. I just want to invite Claire Mao and Adarsh Arasu to come up for a little presentation.
Hello, my name is Adarsh from the Build a CubeSat course. On behalf of all of BWSI, I would like to thank you very much for your talk. It was extremely insightful and eye-opening. I will make sure to take this knowledge and discover your passion for STEM and the importance of self-confidence, as well as your research opportunities you've talked about into my future. And I'm sure all of us will.
Hi, I'm Claire. I completely agree with what Adarsh said. I mean, I thought your talk was really inspiring, especially as someone who's interested in engineering, but also sometimes I doubt my abilities. And it was also awesome to hear about working with CubeSats and the importance of space technology being able to help people on Earth. So on behalf of the CubeSat course and all of BWSI, I would like to present this virtual t-shirt for you. Thank you so much.
Thank you. I hope this helps. And as I said, the main thing you have to do is believe in yourself and look for those opportunities. The internet is a great place, and you just have to be patient, because you're going to see a lot of things that aren't actually helpful, but you can find the opportunity and you can do this.
Thank you.
Thank you so much.
Thank you.
Thank
Thank
you.
you.
So much.
Thank you.
Thank you.
Ms. Apodaca.
Thank you.
Hi, yeah. I actually had a question that I was really dying to ask. I was wondering if I could ask it. Yeah, you're actually muted.
I'm still here. You can ask.
Perfect. Thank you so much. So I was wondering, critics of exploring space, extraterrestrial territories like Mars would say that we should focus more on studying Earth sciences like climate change and geology, biology, instead of studying other planets. And, so my question is, how would you respond to them given your enthusiasm and understanding of cosmology and these kinds of sciences?
Yeah, thank you so much for asking that question. And I think it's a question that if you're interested in this field will haunt you forever. And I think the best answer you can give is space exploration touches an inherent human need to explore, right? Like we have always wanted to know more and go further and learn new things, right? So the thing is, when we decide to do something as challenging as go to Mars, the technology that we need to develop in order to do that is huge. It's enormous, and in a way that we don't even know what sort of impact it's going to have. The best way I have to exemplify this is digital cameras. Digital cameras were originally designed for astronomical purposes. They were used to look at stars. And now imagine seeing this whole conversation without being able to see my face. It's crazy the applications that technology, once it's out there, can do. And that is something that we can't predict. And the only thing we can do is give scientists a project that is exciting enough that they're willing to push and work as hard as possible. And then we also need scientists that, now that we have that technology available, we're also asking ourselves, how can we make this and use it to do better? Like, I'm not saying we have to do one over the other. We have to do both. And there's luckily enough people that are smart enough and interested in both of them, right? So there's no need to think that you can only do one or the other. We can do both. And we have to do both in order to solve the big questions, like how do we, stop climate change?
Wow, I see. That's a really awesome, response. I don't really doing both. That's very, very cool. And then just as a fun question, this year I took mechanics and E&M, electricity magnetism. So when I go to college, I can go straight into second year courses, right? So I'm curious, what second year physics courses do you recommend I take?
Ooh. So my program was different, right? Because I did it in Mexico, and the way it works in Mexico is our first 2 years were all math courses. And then the next couple of years you do physics, right? So I think the first thing I would do is get those math courses in, because they're going to make your physics courses that much easier. You're going to hate the first couple of years, but then everything will just be so much easier. And again, I think also getting all the skills that you need early helps. So any sort of programming class that you can take, any of these will help you in the future.
Got it. Thank you so much.
Okay, I think we should let